Exactly. All right. Good morning, everybody. So I'm Thomas. I'm a senior data scientist at a company called Quantum Black, and today I want to talk about how you can actually get better model performance with less data. And the reason I want to talk to you about this is because so my firm is a consulting firm, so I deal a lot with non-technical stakeholders, and very interesting. So they always come to me and they say, "Hey, Thomas, so." I have like 20, 30, 40 different data sources scattered around my business landscape. Can you please connect all the pieces together and tell me how all of that relates to this one single variable that I'm actually interested in?" And if you follow that guideline, you kind of end up with really bloated models in very complicated situations. And what I find is that a lot of clients, a lot of non-technical stakeholders, they tend to think that more data is actually always better. And I think in a sense this is true, especially when you think about the number of samples. If we have more samples, we can learn more. But I'm personally not so convinced that this is always the case when we think about the number of features, the number of variables you have in a data set. And I don't actually think this belief is just, it is just that non-technical people think this. I actually think in our line of work, a lot of data scientists tend to think like this as well. I unfortunately don't have the exact link here, but I think a week or two ago I was reading reading a blog post from some prominent engineering team, and they were basically discussing, they were talking about how they built their model, and they basically said, yeah, and when we did feature engineering, we created as many features as possible so that we can allow the model to learn all the complex relations that are actually present in the data set. And I mean, this may or may not be true, but I think people that have worked with me will know that I tend to be a very skeptical data scientist, and I think that as a community, I think we tend to think that machine learning algorithms are smart, sophisticated algorithms, but I actually think you can fool them very, very easily, and it is because mainly because of two reasons. I think it's sometimes easy to fool algorithms. The first reason is feature collinearity. So there's a lot of if you have a very big data set with many variables, you'll find all kinds of weird correlations. I think the chances are high you will find all kinds of weird correlations in that data set, and these correlations tend to trip up your models. And another thing is scarceness of data. The thing is, these kind of weak correlations, if I can call them that, your models can detect them, but you typically need a lot of data to actually be able to really measure those kind of really weak correlations between those variables and your target variable. So scarceness of data is also a reason of why it's not always a good idea to always just build as many features as you can think of and plug that into a model. So really what I want to do today is, besides convincing you that it is sometimes a good idea to do feature selection, also talk a little bit about how you can do feature selection. And I will go into the details of some algorithms and also highlight some open source Python implementations that are out there, so that it's basically what I want to show to you all is that it's actually very easy to do this, and it's almost a shame if you not do this as part of your model development process. But really to just highlight the reasons of why it's good to do feature selection. I think one reason is very simple. Less features means you have less data to process, and therefore the computational burden your learning algorithm imposes is less. So that's a good thing as well. The second thing is already what I sort of talked about just a minute ago is to reduce the risk of overfitting. Doing feature selection, limiting yourself to a good set of base variables will help you to reduce the noise in your data set, and therefore allow your model to learn to properly pick up on the right relationships that are present in your data. And finally, this may or may not matter in your use case, but in my use cases, it typically matters a lot because I deal with stakeholders that want to understand what their models are learning. If you have fewer variables in your data set, it will make it easier to explain actually what you're doing, and secondly, what your model is actually learning. So that's on why I think it actually pays off to do feature selection. So let's think about these feature selection algorithms, right? What do we really want from an algorithm? So I just want to like highlight that here. I think this slide really, I think this actually like speaks for itself, and we all kind of know what we want out of this. But really, a feature selection algorithm should first and foremost remove variables that contain absolutely no information that is relevant to your target variable. But secondly, it should also reduce the overlap in information between the variables that you actually select. In the sense that I can have two identical copies of a variable. And if I have a feature selection method that just looks at one variable and tries to measure like how relevant it is to the target, that would select both variables, but they're the same, so they don't contain any extra information. So you would preferably still want to remove one of those two. So that's really what I mean with the second one. And why I think this is important is because like what I've seen a lot is when people actually do feature selection, maybe they tend to like look at what's available in scikit-learn. And scikit-learn actually has some good feature selection algorithms out there, but a lot of them are univariate feature selection methods. And what I mean with that is that they only look at the relationship between a covariate and the target variable in isolation. And I don't think this is necessarily a good idea because I have like two short examples to like really like. To get these points across, even if two variables on their own do not have a strong relationship with the target variable, combining them might actually give you something that does allow you to explain your target variable. And secondly, even if two variables are highly correlated with each other, that does not necessarily mean that that there's absence of what's called variable complementarity. And just to really like drill that message home, I have two very like simple dummy examples, but it does show basically what's happening. So this is a scatter plot matrix of two variables. So if you look at the univariate, if you look at the histograms of each variable, you basically see in the top left corner, this variable is on its own like pretty much useless to really separate your target variable, and the second one sort of separates the two classes, but not completely. This on its own could help you a lot, but it doesn't completely allow you to separate the two classes. But if you look at the two together, you actually see that I can just draw a linear line between them and completely separate them. So again, just a simple example to show that two variables that on their own cannot completely separate the variable can combine to separate the target variable. So this is one reason to not only consider univariate methods, but multivariate methods. And the same for my second point around that high variable correlation does not mean the absence of information complementarity. Here again, you have two variables that are very highly correlated with each other. They sort of like contain some information about the target variable, but again, combining them allows you to completely separate the class. So really, like just two examples that I wanted to show to really illustrate that it pays off to not only look at univariate methods, but at multivariate feature selection methods. So what I want to do today is basically go through this diagram, because roughly speaking, you can divide feature selection algorithms in sort of three categories, and these categories are called wrapper methods, filter methods, and embedded methods. And I want to go through these three methods, quickly explain what these methods are, and give an example give an instance of an algorithm that falls into these three classes. But I'll be coming back to this slide, and basically what I want to do is I want to sort of fill it in as we go along. And I want to start with what are called wrapper methods. So what do wrapper methods do? Basically. What the wrapper methods does, there's a learning algorithm, and you give the learning, as always, you give the learning algorithm a bunch of features, and you basically the decision as to whether you keep a set of features or not is purely based on the performance of that model on some kind of holdout set or some kind of cross-validation procedures you have in place. So an example of this would be you having maybe like a logistic regression. You measure the performance on a holdout set, and you just do multiple iterations, and in every iteration you feed a different set of variables into the model, and you just keep the set that results in the highest performance. So it's a very performance-based measure. Basically, it's really saying, okay, given the learning algorithm, what are the variables that give me the highest performance? Let's just keep those. That's the gist of it. So, you know, sounds pretty straightforward. And again, like if you look around on GitHub, you'll find like open source implementation of this. It's actually like really straightforward to implement this yourself. Like what I just described is more like an exhaustive search strategy where you try as many combinations of features as possible and see which ones work best. But you actually can use different methods here. Like so there's this package called ML Extend. And basically what they have a number of implementations, but one of them is this SFS class, and which basically stands for sequential forward search. So that is just like one variable at a time. We add the variable that we think gives us the most performance gain to our set of selected variables. But as you can see, and this is and almost all of the examples that I'm discussing will have this sort of like scikit-learn like API. So it's very easy to just take these modules and plug them into your existing model estimation pipeline, which you can see here as well. So these are just wrapper methods, like purely performance-based. Which variables give me the best performance on some kind of holdout set? So, which is really its main advantage. Like if you purely care about performance, this is probably going to give you like the best feature set. But there are some disadvantages in the sense that one, it is specific to the learning algorithm you actually use, and two, your wrapper methods typically estimate a new model for every like configuration of the variables you're trying. So the computational burden is actually like pretty big, especially if you think about you having very large data sets, or you wanting to try also different hyperparameter configurations and all these kinds of things. So something to take into account. Now, the second type of feature selection method is what's called a filter method. And the interesting thing about filter methods is that they are actually sort of learning independent. They do not use a linear model or random forest or anything like this to figure out if a feature contains information that's relevant to your target variable. It uses a statistical measure of some sort to just figure out, hey, does this variable add any information to the set of variables I already have? So a very, very simple example of this would be, I have my data set, let's just compute the correlation for every variable between every variable and my target variable, and keep the ones that have a correlation higher than, let's say, 0.8 or something like this, right? That would be a very, very, very simple example. But I don't really want to talk about simple examples here. So what I want to do is I want to go a little bit into the details of one specific instance of these filter methods. And it's an algorithm that is based on a measure that is called mutual information. So if you don't know what mutual information is, I've displayed it here, but really what you need to know is, again, it is a measure that tries to quantify how much information one variable contains that is relevant for the other variable. And you can compute it through this integral, but really what you need to know, the higher the mutual information, the more variable x, the more information variable x contains that is relevant for variable y. So in the context of feature selection, what we really want to do is like make that number as high as possible, right? Like let's think x is the set of features we care about, and y is the target variable of interest. We want to make that mutual information as high as possible because those features x should explain the target variable y. So that is really like what we want to do in our feature selection program, right? Like we want to, again, just to reiterate, we want to select the set of variables such that this quantity is maximized. So that seems straightforward, but it isn't, because the problem is this is an NP-hard problem, because the set of possible combinations of features you can consider grows exponentially. So you cannot like just, it's only in like very basic instances you can solve this thing exactly. So what we really need to do is resort to heuristics, resort to approximation methods of some kind. So you'll find that if you dive into the literature, you'll find that a very popular heuristic is to use a greedy search algorithm. And what you do is very similar to the ML extend example that I just showed. Is incrementally we're gonna add one feature at a time, and the feature we're gonna add is the one that sort of is gonna give us the highest increase in this joint mutual information term we were looking at. So really, this just formalizes that, right? We have a collection of at a given iteration, we have a collection of variables that we've already selected. Now we want to add another variable to that set, and we do that in such a way that we take the variable with index I such that this mutual information term is maximized. Still, we now have to compute this thing. Still, this is very, very hard. So what you can show, and I'm not going to show that here because that's really out of scope, but it's actually not that hard to do it, is that you can decompose that term as follows. And the nice thing is now that here you have a univariate like mutual information term, and then another term that is sort of left over. And this term is still problematic because any term that involves sort of this set S at time point t minus 1 is still a t minus 1 dimensional integral. So you can imagine that as the number of iterations grow, as we iterate further and further and further, it's going to become harder and harder and harder and impossible to actually calculate this thing. So what you will find is that to actually still do this, you will still need to come up with some kind of approximation to these two terms. And how people tend to do that is by basically assuming some kind of linear combination of univariate mutual information terms to approximate that big multidimensional integral. And so this is the linear combination. This is the combination. These two parameters alpha and beta, they're constants. I'll get to them in a minute, so bear with me. But the nice thing about these filter methods that try to do this with mutual information-based measures is that you can now sort of see this sort of trade-off appearing, because the term on the left-hand side where I wrote relevancy tries to measure how relevant a given feature is to the target variable of interest. So that's the relevancy term. But this term is basically a correction term. What it tries to do is, okay, I have this feature that I potentially want to add to my existing feature set, but let's measure how much information that I already have in the set of features that I selected is also contained in this new feature. So it's really trying to trade off, okay, how much new information is my variable going to add versus how much of that new information is actually already present in the set of variables that I've already selected. And the nice thing is that with these parameters alpha and beta, you can control that kind of trade-off. And you will see that actually these parameters, they parameterize a whole family of mutual information-based methods. So if you just take the averages, so these are t minus 1 terms. So if you take alpha and beta to be equal to 1 over t minus n, you basically get an average here, and that the criterion you then get is what's called the joint mutual information criterion. But you can actually play this around because because this is like, again, this is another tricky term to compute. So if you are fine with sort of ignoring this conditional dependency, you can set this to 0 and only look at the trade-off between those two terms. And that's actually what's called the maximum relevancy, minimum redundancy criterion, because you try to maximize, the relevancy of a given variable to the target variable of interest versus how much information is actually redundant in that variable. And then finally, you can also just set these constants to 0 and really only do relevancy maximization, which is not, in my opinion, the best thing to do. But maybe you're time constrained, maybe you're computationally constrained. Then this is another method you can do. And this is actually like the lower one is the one you will be able to find in scikit-learn. So this is it. But so I went a bit into the details of this algorithm just to sort of give you a flavor of what is going on. But really, what I think the most important message of this is if you look at these mutual information-based measures for a filter-based feature selection, what they try to do is sort of trade off the relevancy of a variable versus the redundancy of the information in that variable, and you can actually control that trade-off, which is something I quite like. So again, you don't have to implement all these formulas by yourself. There are actually many implementations out there. There's it's not so sharp, but there's a package called scikit-feature, which gives you a scikit-learn like API, and it actually implements all these criteria that I just mentioned, that whole family, and actually a lot more things as well. So definitely worth a look. Then there's another package called MIFS, which stands for mutual information-based feature selection, which also it's just another implementation of this specific type of algorithm. And scikit-learn obviously also has its own range of feature selection algorithms, some of which are filter-based feature selection methods. And finally, you have ML-extend, which also has these kind of methods in place. So as you can see, like there are actually like a number of different modules out there that you can use. They all have a scikit-learn-like API. So it's if you're comfortable with that already, it's very easy to just plug this stuff into your existing pipeline. So again, like we're coming back to this slide, right? We have feature selection algorithms. You can divide them into 3 categories: wrapper methods, filter methods, and embedded methods. And we've talked about wrapper methods, which are purely performance-based, and we've talked about filter methods, which are almost like the opposite. You do not use a learner to figure out what the relevant variables are, but you use some kind of statistical measure, whether that is correlation or mutual information or some other kind of measure you have. But it's learning independent. So that's kind of like its advantage, you know? It's like independent of the learning algorithm. It tends to scale a little bit better to higher dimensional methods, although there is definitely a trade-off here, especially in the context of what I discussed just now with like the multi-dimensional integrals. But at the same time, I think its strength, the fact that it's independent of the learning algorithm, can also be its weakness, you know? So again, it really depends on the use case at hand. Like if you really care about performance, if that's all you really care about, then maybe you kind of want that interaction to be part of it. Which is actually like a nice follow-up to the final class of feature selection methods, these embedded methods, because they are sort of live in between wrapper and filter methods. What embedded methods, they're a big group of techniques that basically do feature selection as part of the model construction process. You know, you can think about a random forest kind of doing, or a lasso model. I think a lasso model is actually like a better example. That kind of does it as well, right? You train a model. You try to look at you tune the parameters in such a way that you get optimal performance of some sorts. But it does feature selection as part of its learning through the L1 penalty you put on the coefficients. But I don't want to talk about lasso because I think like we're all quite familiar about lasso. I want to take it like one little step further and discuss a method that I actually have found pretty useful. And this is is a method called stability selection. So what is stability selection? It is an algorithm that wraps around an existing algorithm, much like a random forest actually does, right? A random forest is basically like estimating a decision tree, which is your base learner, on multiple like bootstrap samples of your original data set. So stability selection is actually not that dissimilar from this approach. What happens is you have stability selection, it wraps around another algorithm. The one thing that other algorithm needs is some kind of parameter that controls the amount of regularization you put on the problem. And I am gonna use the lasso in this example, but actually like stability selection is an algorithm that is actually is model independent. So you can do this. You can do it on lasso. You can use it on orthogonal matching pursuit algorithms. In theory, you can do it on gradient boosted trees and all this kind of stuff. So it's actually like quite model agnostic. But it was introduced in the context of lasso models. It was introduced in the context of genetic problems where you typically have very low sample size and a very high dimensional data set. But to get back to the algorithm itself, so you have a base learner, and what the base learner does for every value of the penalization parameter, you basically get a set of variables back, right? So think about lasso for a given value of the L1 penalty, you're going to get a set of variables that the lasso model actually deems relevant for your particular problem. So here it's exactly the same. So what does stability selection do? It takes that base learner and it runs, like a random forest, it generates many bootstrap samples of your original data set, and it's gonna run your base learner for a grid of values of that penalization parameter that you have on every bootstrap sample. So you're really you're gonna, and this is why actually you want this base learning algorithm to be computationally cheap, right? Because you're gonna estimate this model for many times actually. And really, and what you sort of do is, because you get the bootstrap sample for every value of the penalization parameter, you get a set of variables that is relevant. So what you can then do is compute, basically you keep track of which variables get selected, and you can actually compute some kind of like probability of your variable being selected or your variable being relevant. So really, like, I hope the diagram makes what I'm just describing to you in words a bit clearer. But really what happens is, right, you have, we iterate through every bootstrap sample and for every value of the penalization parameter. What we do is we generate the bootstrap, we estimate the lasso model, we keep track of the features that get selected. This we do many, many, many times. Once we're done, we can actually compute the probability of inclusion, and then we sort of select a set of variables that exceed some kind of threshold. And the idea, so what is really the idea behind this method, right? The idea is that you typically have a high-dimensional data set, and you really want to figure out which variables are really, really relevant for my problem. What I do is I create many copies of my original problem, and I inject noise in every copy of that problem. That is what the bootstrapping does, in a very similar way as to what random forests do. And the idea is that, hey, variables that are relevant are variables that are going to be deemed relevant in every one of those subproblems, even though there is extra random noise injected into that problem. So that's really the idea. In the presence of all this injected noise, which variables are still relevant? So actually, like, it is actually quite straightforward to implement this kind of model, because it's really just like generating some bootstrap samples and estimating a model many, many, many times. So I've just like outlined the base like implementation here. So really, what the idea is, right? We iterate through a grid of penalization parameters. We iterate through a number of like bootstrap samples. What do we do? Right? This is the first block. We generate the bootstrap sample. We set the tuning. We set the L1 penalty, and then we train a model. And in the end, we keep track of only the variables that actually get selected. And then in the end, it's to actually compute the score. It is a very simple mean over the proportion of how often these variables get selected. So this is a homegrown implementation. I just wanted to show it to you that it's actually like very, again, straightforward to implement this. There are better implementations out there, especially if you look at R. Like R has a strong following in genetics. So there's a package called STUBS, which stands for stability selection, and they have a pretty decent implementation of stability selection in there. Then there's also a Python module called skggm, which what it really tries to, it has actually a scikit-learn API, but what it deals with is basically Gaussian graphical models. But as part of that whole suite of methods that are relevant for that class of models, they actually also have an implementation of this stability selection procedure. So again, the methods are out there, right? And everything, and it's quite nice that as a community we've sort of like converged on the scikit-learn API, so it's very easy to just plug and play with these kind of components. So I would definitely recommend to have a look at these methods. Yeah, okay. So now we're here. This is basically what I wanted to do with you today. I wanted to give you a full overview of the sort of type of feature selection methods that are available, and sort of highlight highlight one, what they do, two, give you an idea of what algorithms in that specific class look like, and three, give you a feeling of the advantages and disadvantages of these methods. But really, if you think about it, you have wrapper methods that are purely like performance based. You have filter methods who are sort of on the opposite end of the spectrum, who are not really performance based, but really think about it in more statistical terms. And you have embedded methods that sort of sit in the middle of these two like classes of methods. And it really depends on the use case. It depends on the use case you have. It depends on the data you have, how much data you have, and all these kinds of things as to which like method is best for you. Again, as always, there's no silver bullet, no one method to rule them all. But but at least this gives you sort of an idea of, okay, these are the strengths of these methods. If I want performance, I will probably want to look here. If not, maybe I want to look here, etc., etc. which kind of brings me actually to the end of this presentation, right? It's like this just reiterates what I was just saying. Like, I think very, very generally speaking, filter methods tend to be a bit faster than embedded methods, and embedded methods tend to be a bit faster than wrapper methods. Just because wrapper methods, they estimate a model for every different configuration of the variables you have. And in terms of overfitting, you'll find that wrapper methods, they'll have higher learning capacity because therefore they're a bit more likely to overfit than embedded methods, which are a bit more likely to overfit than filter methods, just because filter methods tend to not be connected to the learning algorithm you're actually looking at. But again, this is very generally speaking, and it really depends on the specific use case as hand, because I'm talking about overfitting. But if you're really in a case where you have large and larger amounts of data in terms of the number of samples, this overfitting risks becomes there's less of that kind of risk. Whereas if you're in a low sample size case, the risk is actually much higher. And which is also why, if I think about how I tend to use these methods, if I'm in a low sample size case, I tend to look at filter methods and embedded methods. Whereas if I have a lot of data, I tend to more look at embedded methods and wrapper methods. So really, that's all I wanted to do today. I just wanted to give you all a feeling for these methods. I hope the message hit home. And if there are any questions, I'm more than happy to answer them now. Thank you.
Do you find that this feature selection reduces your need to do that, or do you still have to do all of the combining?
I think it's a very interesting question. So I think it's a bit twofold, because initially I found that I still need to do that just to make them a little bit happy. But the kind of power is then that I do that, I apply these methods, and then I show them that only a very tiny portion of their data is actually either relevant or in a good enough shape. It's typically the latter, because the data is so poorly collected that it's actually relevant. And then you'll find that in the follow-up after that, then I have more credibility in that sense to just say, hey, we did this in the past. This is not how it works. We should first zoom in on a couple of things we a priori deem very, very relevant, start from there, and then see if we can add and all. That's typically my approach to these kinds of problems. Sorry. Yeah.
Very good overview. My question is around categorical data.
Yes.
Features. How do you deal when you have a lot of categorical data?
So if you think about it, it should actually not really be a problem, because this mutual information term, when it becomes a categorical variable, it becomes a sum. So it's actually much better for you, to be honest. So what you'll find in the filter methods case, it just depends on the measure. So mutual information-based measures, fine. Correlation, not so fine, right? And then if you think about the embedded methods and the wrapper methods, they are based on the learning algorithm. So it's really up to, can your learning algorithm properly deal with categorical variables, and then you're good, yes or no. So in the case of stability selection, you're totally fine, because it's a lasso model, and that totally deals well with categorical variables. So that becomes more important.
How do you deal with categorical variables with high cardinality?
Mm-hmm.
Do these things tackle them out of the box? So typically, you want to treat that feature as a separate feature, rather than what normally goes into the models is a one hot encoded mass.
I totally see what you're saying. So I do think my answer is going to be very similar, though, because with the wrapper and embedded methods, it's about the learning algorithm. So it's about the capacity of that algorithm. Can it deal with these variables of high cardinality? And then I think the question is the filter method. So I've actually not tried these methods on that kind of problem.
So typically you want to keep, so if it says that feature X is important,
mm-hmm.
You want to keep all of
the whole thing, and not just the one indicator of that one level. No, I'm totally with you. So no. But the filter methods will do it, actually, because it just again depends on how you construct your original data set. But if you keep it as, let's say, one column in that sense, it is one integral that it's measuring, and it computes the integral by looking at all those different levels. And it's not even a hard integral to compute because it becomes a sum because because it's discrete. So like even if you have very high cardinality, that should totally be doable. So actually, in all honesty, I've not used it on those kinds of problems, but I actually think it should not for this particular type of filter method. I don't think it should be a problem. You can, because it just becomes it still becomes an integral of that variable of high cardinality with the target variable. That's fine, and for the wrapper and the embedded methods, it depends on the learning algorithm. So that would be my answer. Cool. All right. Thank you, everybody. Sorry.
I really like the example you gave of the example that motivated looking at two together rather than the university.
Yeah.
It did make me think that maybe that might be a job that unsupervised learning could be quite useful at. I think that's it's a general example of filter methods, perhaps. Is that something you've explored in terms of how unsupervised approaches might help?
So is the question then that you have a data set, and is the question then, did I try first doing some unsupervised method to maybe learn some kind of embedding and then do feature selection on the embedding? I've not done that. So I've not done that myself. I don't see a reason why it would not work. The only thing is it becomes hard to then link it back, I think, to your original data set, depending on like the unsupervised method you use, right? So I think that would be my own, I think to me it sounds like this is totally doable, but this is the only piece of the puzzle, which for me personally would be a problem because I tend to have to explain what happens in my model. So if I then have this unsupervised block in the middle, it becomes kind of tricky to link it back. But in principle, I don't think this should be a problem, but I've unfortunately not explored it myself yet.
Did you have we've been saying a lot about explaining to clients and kind of things. If you had experience where you did this feature selection and it was telling this one's actually completely rubbish, you don't need it, but yet a lot of people around you were convinced it is the one to use.
Yeah.
How did you deal with that?
Yeah. So this has definitely happened to me. So this is a very tricky situation. So that really becomes more of a soft skills problem. How do you communicate this to your client? How do you manage that? So typically, I've definitely encountered this. Typically, what happens is we do a couple of follow-up analyses, looking at that variable in particular, and we're trying to understand. Okay, is what we're seeing, is that truly correct? Is it one, truly that the variable does not add any information, or is it that the information that we thought is present in this variable is actually already present in this other set of variables that we actually have selected, right? Because if it's that case, then we're kind of done and we have an explanation for it. And if it's not that, then really what we need to do is we need to dive into that variable and try to understand, okay, a priori we thought it was very relevant, why is it not relevant? So then it becomes just a matter of investigation, really.
That's fine. Let's speak on that.
Thanks.